Good afternoon, everybody, or good morning, whatever you are. So this is the live streaming of the second, maybe the first official of a talk of machine learning for science series. And today our speaker is Alessandro Lunghi from Trinity College here in Dublin. So Alessandro graduated in chemistry from University of Florence about 4 years ago, and then he moved to Dublin, where now he's a senior research fellow, and his main interest is in materials modeling, in particular spin models, and also to
Okay, thank you, Stefano, for the introduction. So today I'm going to talk about spin-Phonon relaxation, as you said, in molecular materials, and I'll show you some of the application of first principle calculations and machine learning on this topic. Now, before I go into the details of the topic, I just would like to try and answer the fundamental question why we should bother studying spin. So spin is a fundamental property of particles. It's a quantum properties. So essentially, there is no correspondence in classical mechanics. So it sounds like something exotic, but it's actually a very common feature of matter. And for instance, is the building block of magnets. So if you think about bulk iron, essentially the magnetic properties of iron comes from the fact that there is spin in the electron. And the same, you also, if you start shrinking the sizes of magnets, if you have nanoparticles of paramagnetic molecules, still all the properties come from the fact that the electron bears a spin. And if you combine magnets with electronics, you get spintronics, which is something that we have spintronic devices in our computers. So it's something that also technologically it's important, but also protons have a spin. So for instance, magnetic resonance imaging, like the one you see here in this picture, it's possible because proton has a spin. More trendy lately, also quantum technologies. Essentially, as I'll show you also later, we can use spin in a quantum fashion to implement quantum logic. And this is actually the focus of this presentation, if you want. So in a nutshell, what quantum computing is. In a classical way, if you have a magnetic object, you can polarize the spin or the magnetic vector upward. And so you can say you have a zero state, or you can polarize your spin vector downwards. And so you can say you have one state. So these two states essentially are the classical bits that you have in hard drives, in magnetic hard drives. In quantum computing, you try to make a step forward. So instead of just using the 0 and 1 of spin, you also superimpose these two states in a coherent way, and you try to exploit the quantum properties of spin. This is something that has been also realized experimentally. You see here a recent example. Here we have two rings, two molecules that bears a 1/2 spin, and it's possible to connect these two spins and manipulate them with external stimulus like microwave radiation and implement quantum logic. In this particular example, they implemented the CNOT gate. Now, going from this very simple example here to a device, there is a long road. There are a few fundamental challenges. The first one is that we would like to have long coherence times. So what it means, so essentially when you create a superposition of these two states, 0, 1, you create a coherent state, but this coherent state has a finite lifetime. So if you wait long enough, the coherence disappears and you're back to the classical case. So your quantum computer stops being quantum essentially. So you would like this coherence time to be as long as possible. Then you need to connect different qubits. Here you've seen the example with two connected qubits, but in principle you would like to have a scalable architecture, so you would like to connect as many spins as you want. Then you need to be able to initialize the states, manipulate them, to implement the logic, and then read the results of your calculation. So all of these challenges are important on themselves, but today we're going to talk mainly about long coherence times. So if you want, the sine qua non condition for observing this phenomenon. Okay, let's see a classic experiment in magnetic molecules. So what we are interested in principle is T2, the coherence time, but we also need to monitor T1, and I'll explain you why. So in this plot here, you see these two times, T1 and T2, as function of temperature. This is a very common experiment. So we measure T1 and T2 as function of temperature, and we see where is the bottleneck for these processes. So you see T2 is almost constant here at low temperature, But however, if you increase temperature enough, eventually T1 becomes the bottleneck for coherence time as well. So T1 is going to be the target of this presentation, and it's important to understand which are the processes behind T1 if you want to operate quantum computation at ambient temperature. So in a nutshell, what T1 is, so let's say we have two spin 1/2, so we have two spin levels, 1/2 and minus 1/2. If we are in external field, the degeneracy of these two levels is split by the Zeeman interaction. And as soon as you start manipulating the population of the states, let's say with microwave radiation, the system will start interacting with the phonon bath in order to reestablish the equilibrium, the thermal equilibrium. And this can occur through several processes, direct relaxation, Raman relaxation. And so it's natural to ask ourselves the question, how these processes work. So can we learn something about this entire process here and see if we can tune T1 and increase it? Let's see what we know about these processes here. Well, the answer is not so much. So if you, for instance, refer to this paper here from 1983, you see that the relaxation time depends on temperature as a polynomial, where the exponent of T temperature can be 1, 2, 3, 4, 5, 6. It can be 7. It can also be 9, but it can also be exponential. So essentially what I want to tell with this slide here is that we can expect a very complex behavior of relaxation time as function of temperature. And this is a problem because if we just measure relaxation time as function of temperature and we fit a polynomial relation, we have no idea what's behind these coefficients here that we are fitting. So we don't know what's the physics behind A, B, or C and X. But this is exactly what we need to know if we want to improve these molecular magnets. So we need to have a microscopic understanding of what's going on during relaxation. So let's say our end goal is to engineer spin-phonon coupling, increase T1 as much as possible. So I would say there are three fundamental steps in this direction. So the first one, understanding the physics behind spin-phonon coupling. Then we will need to connect the physics to the chemistry. And then once we know where to look for new molecules, we actually need to find them. And so this is the problem of design of new molecular qubits. So the presentation is essentially structured along these 3 points. I'll start with the first and then proceed with the rest. Okay, so let's start with the first one. We want to understand the physics of spin-phonon coupling, which means that we need to implement a first principle theory of spin relaxation. So let's start from the very beginning. We have an Hamiltonian, H, that is going to describe the entire physics of our problem. The first term is HS, the spin Hamiltonian. So let's imagine for the moment that we have one single spin, one half spin, isolated. Its own level structures, it's going to be described by the Zeeman interaction in external field. Then we have to model the heat reservoir, the path that the spin interacts with and gives away the excess of energy that it has. This can be described in solid state with an harmonic approximation of the phonons. So we have a lattice, the atoms that surrounds the spin are going to vibrate with a given frequency omega. And at a given temperature, we're going to have each mode populated by the value here and alpha. If you're picky, you can also include anharmonic interactions. So essentially, these are the phonon-phonon scattering events that also reduce the phonon lifetime and include higher order interactions in the lattice. Finally, we have the spin-phonon coupling Hamiltonian, which is the term that makes the spin interact with the lattice. So far, there were independent systems. Thanks to this term here, you can have an exchange of energy between the two. Usually, what we do at this stage is to invoke the weak coupling regime. So we model the spin phonon Hamiltonian as a Taylor expansion of the spin Hamiltonian, HS, with respect to the normal modes, so the vibration of the lattice. So essentially, the atoms are going to vibrate at a given temperature, and these vibrations are going to modulate the spin interactions. So this is essentially the fingerprint of the interaction between the two systems. So we said we want to assume a weak coupling regime, so we can start with a first order derivative, and if it's important, we can also extend the studies to second order derivatives. So this is the shape of our Hamiltonian. We described the dynamics. So now next we can try to get some equation of motions for the spin embedded in the lattice. So let's start with first order perturbation theory. To do that, we neglect the second order derivatives. So we restrain ourselves to the first order case here. And then we make the fundamental assumption that the path is going to always stay in equilibrium. So this means essentially that if the spin wants to release some energy in the bath is able to accept this amount of energy without increasing its own temperature. So essentially we are saying that the dynamics, the dissipation dynamics of the bath is extremely fast with respect to the one of the spin, which is usually the case for the systems. Under these approximations, what we get is the Redfield equations. So you see here PdA is derivative in time, where PdA is the population of a spin level. So let's say it's the amount of population of our system that is 1/2 spin or minus 1/2. And as you see here, the rate of change of the population is given by a summation on alpha. So in principle, every phonon in the system is able to contribute to spin relaxation. And each phonon is going to contribute with a term that is the multiplication of these three factors here. So the first one is the coupling to the lattice. Then we have the selection rules, and finally the lattice green function. So now I'm going to go through these three terms very briefly just to explain what's the physics behind. Okay, so we have in blue here, it's the coupling, the spin-phonon coupling essentially. So you see here, you have G, that appears in the spin Hamiltonian, and this is intrinsically dependent on the position of the atoms inside the molecule. So during the atomic motion, this term is going to be modulated, and that's why we have a derivative here. And essentially, it sets the intrinsic transition rate between two states as modulated by the phonon alpha. So larger this term, more coupling between the spin and the given phonon there will be. So this phonon will be more important for the spin dynamics. Then we have in red the selection rule, which is not very exciting in case you have just two levels, but it's been proved to be fundamentally important for a system with a larger spin. So in case you have many spin levels, so you're not just an S equal to 1/2, but let's say you have an S equal 15/2, you can play around with this term and select a symmetry of the spin Hamiltonian in order to avoid the direct transition, like in this case, or in this case, but force the spin system to cross the entire magnetization reversal barrier and slow down the relaxation. Finally, the lattice green function. This is the term that contains all the information about the phonon dynamics, so what happened in the bath. At the first order, it's described by two terms. The first one describes the phonon absorption probability. As you see, it depends on the number of phonons we have available. So at a given temperature, we have a number of phonons. This can be absorbed by the spin, but it can also be emitted in a stimulated fashion. So it depends on the same number. But you see here that we also have this +1, which is of course temperature independent. And this, it's essentially it's there to account for the spontaneous emission of a phonon from the spin. Okay, so at this stage, what we have, it's an equation of motion for the population of the spin levels, which is not a great achievement. Essentially, this is the same formalism used by Redfield and Van Vleck or Auerbach to describe spin relaxation many years ago. But however, the important thing is that this specific equation here, it's written in a fashion which is very easy to be implemented in a first principle fashion. So essentially, all these parameters here, like G, B, all this frequency here, can be calculated with first principle. So we can implement this equation and solve it numerically now. Okay, let's see, there are two fundamental questions that we would like to answer in doing this numerical study here. So the first one is, which is the driving force for spin relaxation? And the second one, we would like to see which are the phonons that drive spin relaxation actually. The guinea pig for the study was this vanadium 4 plus compound here. So we have one unpaired electron spin that is sitting here on the vanadium atom. And vanadium also has a nuclear spin, so there will be a nuclear spin 7.5 interacting with the electronic one. To model these interactions, we need a spin Hamiltonian that contains at least these three terms. The first one is the Zeeman interaction that describes the interaction between the external field and the electronic spin. Then we have the hyperfine, which is the interaction between the electronic spin and the nuclear one. And finally, we can also include the dipolar interaction inside the crystal. So essentially, this is the isolated molecule, but the molecule is extracted in this case from a molecular crystal, which is densely packed. And all these molecules here are in principle able to interact through dipolar interaction. So that's something we might want to include in our picture as well. That was the static picture. We now need to derive the dynamical one, which means we need to calculate the spin-phonon coupling interaction. And what we do, we simply take the derivative of the spin Hamiltonian with respect to phonic positions. And if you look at the spin Hamiltonian, the only terms that depends on the atomic position are these coefficients here, G, A, and D. We can use electronic structure to calculate these quantities exactly as we did for the static ones. So for instance, we can use CAS-SCF level of theory as implemented in ORCA to calculate the G-tensor and the numerical derivatives. Or for instance, in this case, we use DFT still implemented in ORCA to calculate the hyperfine interaction and its numerical derivatives. For what concerns the D interaction, this is just a dipolar interaction. We know the analytical expression, so it's just an analytical derivative in this case here. Then we need to describe in first principle fashion also the phonons. So what we did, we took a supercell, which is this picture here is actually the supercell that we simulated. It was a 3 times 3 times 3 times the unit cell, and we did the calculation with CP2K. So we calculated all the force constants occurring in this supercell here, and starting from those, we can obtain the energy of the phonons and the normal modes across the entire Brillouin zone. So for instance, here you see the energy of the phonons along a given path in the Brillouin zone. You see at the gamma point, you have 3 branches which are zero in energy, which are the acoustic phonons. Then you have the first optical mode at gamma, which sits here, which is more or less 50 wave numbers. And then if you go outside gamma, the acoustic modes, they start having a given value of energy, which is not zero anymore. Okay, so let me recap just briefly the entire procedure. What we do, we use electronic structure theory to calculate spin Hamiltonian, spin-phonon coupling Hamiltonian, and we use in this case DFT to calculate the lattice force constants. And once all these parameters are known, they can be input inside this spin dynamics code that I wrote. Essentially what this code does is to implement numerically the red field equations given these parameters obtained by first principles and solve them. So at the end of this procedure here, you get the spin relaxation rate. And it's important to stress that there are no adjustable parameters inside the entire procedure. So given a level of theory, given the X-ray structure for molecular compounds, you get at the end with the non-equilibrium spin dynamics. So let's see some results. You see here on the left, the relaxation time as function of the external field, while on the right, you see the same quantity, the relaxation time as function of temperature. So in the first case, you see here in blue the experimental results, and in black the total spin relaxation rate, which is due to the Zeeman interaction in high external field and to the hyperfine one in the low external field, where high and low is below or above 5 Tesla, more or less. Now, this behavior here is expected. The Zeeman interaction depends on the external field. So eventually, if you keep increasing the external field, this interaction will dominate the relaxation. And while at the same time, if you reduce this, eventually something else will be more probable. And this is the case for the hyperfine interaction. As you see here, relaxation time in high field, it's not very far away from the experimental one. In the low field, there are 3 orders of magnitude difference. So we expect that there is going to be something else, which we have not included in the model so far, that it's going to overcome the contribution of the hyperfine at the first order. And it's probably going to be a second order phenomenon, which is not yet included. On the right, you see the temperature behavior. If you model the phonons as harmonic, you see here a t to the -1 behavior, which is expected from theory. And you see here at low temperature, the relaxation times reaches a constant value. And in this regime here, essentially the relaxation mechanism is due to the spontaneous emission of phonons from the spin. We also try to model the phonon line width. Essentially, phonons are not always harmonic, but they can also scatter among themselves. And if you include this, you see that you can have some differences in the relaxation time, both in order of magnitude, but also on the, let's say, on the trend with the temperature. So it might be important to come back to this point in future and model it in a more appropriate way. Okay, so let's now focus on what happened in the high field regime here. So we are at around 10 Tesla, which translates in 10 wave numbers. And at this level of energy, only acoustic phonons are available. So the acoustic phonons must be the responsible for direct relaxation in this case. Before going to the next slide, just want to recap what spin-phonon coupling can arise from. So essentially, we have seen the spin-phonon coupling arises from the modulation of the spin Hamiltonian coefficients from the atomic motion. So for instance, if you have a molecule and the molecule gets started for some reason, the spin Hamiltonian is going to change because the crystal field felt by the electrons is going to be different, and this gives a spin-phonon coupling coefficient. The rotation, similarly, would also contribute to spin-phonon coupling because all these terms here, like G, they are tensors, they are anisotropic, and it means that you rotate the molecule, these numbers are going to change. So you have a derivative, and therefore you have a spin-phonon coupling. However, if you have a rigid translation of molecules in space, assuming there are no external inhomogeneous field, this kind of motion here cannot give you a spin-phonon coupling because the G tensor is invariant under rigid translation. However, if you think about acoustic phonons, usually these are thought as a rigid translation. So it seems like that we just said that acoustic phonons are responsible because at the energy that we observe the relaxation, there are just acoustic phonons available, but then acoustic motions cannot give any spin phonon count. So to solve this issue here, we analyze the density of states of the phonons that you see here reported in black. We also decompose these density of states in local translations, rotation, or intramolecular motions. And you see here that you can find these contributions also at very low energy, and in particular at energies which are comparable to the xenon splitting we were observing before. So essentially, what we find out from this study here is that acoustic phonons are not pure molecular translations, but they are strongly mixed with the intramolecular motions. And these intramolecular components, even though it's very small, it's non-zero, and it's what gives you a final value for the spin-phonon coupling in this case here. So let's summarize something about this first part here. So we've seen that first principle calculations can be used to predict spin relaxation rate. We have learned that acoustic phonons are not pure translation movements of the molecule inside the crystals, but they also contain intramolecular components, which is exactly what gives you a final value for the spin phonon coupling coefficients. And if you want to try and guess which could be the new design rule to increase the spin lifetime, in this case, one possibility would be to increase the rigidity of the molecular structures. This would, in principle, diminish this intramolecular contribution to the acoustic phonons, and therefore it's supposed to slow down spin relaxation. Okay, so we have learned something new about the physics behind spin relaxation, but now we would like to make a step further and try to translate the physics into a chemical language. And what we will try to do in the next few slides is to try to understand spin phonon coupling in terms of ligand field. Essentially, the problem here is that when we talk about spin phonon coupling, we can go to a chemist and tell them, you should reduce spin phonon coupling, but then there is no understanding on how actually implement this into a syntactic procedure. And ligand field is a theory that has been used in the past, well, actually for a long time and still used today to interpret, let's say, the electronic structure of coordination compounds. And it's also used to actually give you some possible guidelines on how this happens. So for instance, we know the relation between the nature of the ligands and the crystal field splitting, which is known as the spectroscopic series. And so we would like to translate this knowledge here in terms of also the dynamical processes behind spin-phonon relaxation. So we have published some of these results in these two papers. The first one, it was a collaboration with a group in Florence, and the second one is what I'm going to talk about more in detail today. So in this study here, what I did is I selected this molecule here. So we still have a vanadium +4 as before, but then we're going to study a series where we're going to change the first coordination shell ligands. Now here you have this table, so I'm not going to pretend anybody to read it, but I just want to draw your attention to two facts. So the first one is that the experimental and the calculated parameters follow the same trend for this series, which is good. And the second one is that the calculated G shift also correlate with the spin-phonon coupling in this molecule here. So we have this series here. Now, let's first try to understand what happened to the G shift across this series in terms of the gun field, and then we'll see if it's possible to also say something about spin-phonon coupling using the same kind of language. All right, so first thing we can do is to try to predict the trend of G shift as function of the crystal field parameters. So for this series here, we have only one electron. We're going to expect to be in the dz square orbital. We're going to have a first excited state, which presumably is going to dominate the G-tensor properties. And from electronic structure theory, we can actually quantify the energy splitting between these two levels here. And you see it's reported here for the series, and we have the maximum with sulfur, which is correct if we take a look at the G-tensors. The G shift for the molecule with sulfur is actually the smallest one. And however, if we just include in our description picture, we also need to go beyond the crystal field and include also covalency between the ligands and the metals. To do so, we're going to replace these terms here, these expectation values here, with two parameters, alpha and beta, here at the numerator, and this accounts for covalency. From population analysis, we have seen that actually covalency increases across the series. And if you put these two information together, you can actually now interpret the trend of the G shift across the series. So now we have a relation of the G shift that contains quantities which are in a more chemistry-wise language, if you want. And we can now try to go from this picture here to the dynamical one. So we have the G tensor. If we want the spin-phonon coupling, we just need to take the derivative of this expression with respect to atomic motion. If we take the derivative, we have in principle both the numerator and the denominator that could be depending on atomic position. However, we checked from the simulations that covalency is not dependent on molecular motion, at least for small distortions, which is the regime we are interested in now. So the difference in energy between the ground and the excited states is here the only term that is going to matter when we take this derivative. And if you do that, you obtain an expression which looks like this. So you have the spin-phonon coupling coefficient here, which is, first of all, it's explicitly proportional to the static G shift, which is something we have seen before from the simulation, but we couldn't explain in a quantitative fashion. But we also see that now we have a relation that tells us that the spin-phonon coupling is also proportional to covalency and inverse proportional to the crystal field splitting. So if we want to diminish this parameter here, what we should do, we should try to increase the covalency, because large covalency corresponds to small values of alpha and beta. We should try to increase the crystal field splitting. And as we also seen before, we need to decrease the value of these derivatives here. And this is something we can in principle do by increasing rigidity of the molecules. Okay, so let's draw some conclusions for this second part. So we have seen that the static spin Hamiltonian is proportional to the dynamic one, and so we can use the static spin Hamiltonian parameters as a proxy for spin relaxation. And this is important from an experimental point of view because it's possible to measure from EPR the static terms of the spin Hamiltonian, but it's not directly possible, or at least not so easily possible to get a direct estimation of the spin-phonon coupling coefficients. Then we have seen again that molecular rigidity should reduce spin-phonon coupling, but we have also learned that covalency and large crystal field splittings can also reduce the relaxation rate of spin. Okay, let's move to the third part, which is also the last one, and this is going to be about machine learning. So the problem here is that let's say we have learned something about the physics, we have translated it in terms of chemistry. Now we have the problem that we need to individuate the best molecule that results from the analysis that we've done so far. And in principle, this can be very hard. There are an infinite amount of ligands that you can synthesize. You can combine them with all the transition methods, lanthanides in different structures. So it's not so easy to guess correctly which is the best molecule among all of those. So what we do here, we try to use machine learning to speed up this process and discover new molecules more quickly. In a nutshell, what machine learning is essentially a regression at this stage. So let's suppose we have a series of properties given a structure. We do a regression, which means that we try to get a model that can predict the property as function of the atomic structure. Let's suppose for a second that our property is the conformational energy, and we want to predict it as function of the molecular structure. So essentially, think about a molecule, you can distort the atom positions, the energy is going to change. We want to predict this, how much is going to change the energy. The model that we use, it's called SNAP, was published here in this paper here in 2015. And essentially, it's a very simple model. We have the energy, which is decomposed in atomic contributions. And each atomic contribution depends on a linear relation of this kind here, where beta are parameters that we want to determine through the training of the model. And these capital P's are for these spherical models. And essentially, you can think of this as a fingerprint of the atomic structure of your compounds. So let's say you sit on atom I, you take a look at the position of all the atoms in the surrounding, and then you process the Cartesian coordinates through these functions here. And you get a list of numbers. Those numbers are the fingerprint of your atomic environment. The number of these parameters here can be increased. So this means that you have, let's say, a way to increase the performance of your model, and in principle you can extend it to an infinite number of parameters and give the model arbitrary flexibility. Okay, let's see some results. We tried the first time to apply this model here to this very simple compound. This is an iron plus 3 chloride. So what we did, we took this molecule here, we used DFT to calculate the energy. Then we created some artificial distortions of the atomic positions, and we calculated the energy again with DFT. And this is what we call a training set. So it's a list of energies and the structure related to that value of energy. And this is what the information that we use to train the model. Here in this plot here, you see what is called the learning curve. So you have the error that the machine learning model does in predicting the energy for a given conformation as function of the number of examples used to train the model. So for instance, if we have here 400, it means that we use 400 values of energies and corresponding structures to train the model. And in purple, you see the regression error. And what's important is that here in blue and green, you see the error of the model on predicting the energy of a structure that has never seen before. So essentially, this is the ability of the method to extrapolate to new conformations. So when you're here, let's say we have 100 examples in the training set, the model can get a very good regression of our 100 structures, and that's because we have an excess of parameters inside the model with respect to the amount of information that we want to do a regression on. However, the model is terrible on predicting the energy of structure that are not contained in the training set. So the error on the test set is going to be very large. If you increase the number of examples in the training set, you see that the training set is going to be a little bit worse. And that's because you're saturating the flexibility of the model, but at the same time, the error on the test set and validation test decreases and they reach the same value, which if you look at the value, the actual value, it's extremely small. And why it's important is that because while DFT can take hours to run a calculation and predict the energy, machine learning can take milliseconds or even fraction of milliseconds. So this means that while DFT can be used to study molecules which are, I don't know, maybe 1,000 atoms on a very large computer with a lot of efforts, the same calculation with machine learning can be done on a laptop. And that's why it can be useful to speed up these calculations. So we've tested this approach here on different kind of compounds. So the example I showed you before on very simple coordination compounds. It's nice to see that it can also predict naturally the occurrence of the Young-Taylor distortion. We have tested it on chemical reaction, and it works. Also in cases where you have transition metals involved and spin crossover effects. We tested it on solid-state materials like high-temperature ceramics, tubing materials, and for the calculation of thermal and elastic properties, and it always worked. But today, I would like to show you the results for a magnetic compound. So far we have talked about molecular qubits. Here we're going to shift a little bit the topic, and I'm going to talk about single ion magnets. So essentially the idea here is to use a molecule as it was a classical bit. So we would like to have a magnetic moment that is going to stay fixed in space. Its direction is going to remain fixed in space at any given temperature. And to do that, you need to have an element with a large magnetocrystalline anisotropy, which is labeled T here. So the larger and the more negative T is, the better for this kind of application. So we studied this molecule here, which is a cobalt-2 compound. It was published experimentally in this paper here in 2016. And what we did first is to try to build a model for the energy. As you see here, the predicted energy matches perfectly the DFT1. But what's important here is that we can also extend this model here to other properties from energy, and in particular to magnetic anisotropy. So you see here you have only two wave numbers that are on the prediction of anisotropy. So we have the machine learning can predict both at the same time. Let's see a possible application of these kind of models. So here, what we want to do is to do a fast conformational screening of conformations for this molecule and see if we can get some guidelines on how to distort the ligands in order to improve our property without damaging completely the molecule, of course. So what we do, we design this function here, chi, as this function here is defined as the sum of the energy and the molecular anisotropy multiplied by this lambda here. So if lambda is 0 and we minimize this function here, essentially we are just moving the atoms in order to reach the minimum of the energy. We're just minimizing the energy of our complex. However, if we switch on the perturbation and we chose a very small lambda, what we do, we distort the molecule in the direction that improve the anisotropy. So the anisotropy is going to decrease with the sign minus, but it's going to be larger in absolute value. And the model here, since we are weighting also against the energy, is going to choose the direction which are not energetic expensive for this kind of optimization. We did this by using a global optimization algorithm like particle swarm. And what we found out is that only two intramolecular degrees of freedom are important for this magnetic structure correlation here, and they are reported here. The first one is the distance between the central cobalt ion and the nitrogen, which are the first atom coordinating the cobalt, and also on an angle involving nitrogen, cobalt, nitrogen again. So it's this angle here, if you can see the pointer. So essentially what you see is that if you decrease both of them, you can decrease the energy of 50%, which is a large value. But essentially what this model here is telling us is that we need to increase the crystal field and make it more axial as possible, which is not a great discovery since this is essentially the main guiding light to synthesize new single ion magnets. But what's important here is that we obtain this information without absolutely no knowledge about the physics governing spin dynamics in these compounds here. Essentially, if you can think to apply the same method to a more complicated system for which you don't know anything about the magnetism, and this algorithm is going to give you the best magnetic structure correlation to improve it. Okay, so let's summarize also this third and final part. So we have seen that machine learning can predict molecular properties, usually at the same level of accuracy as first principle calculations. We have seen that machine learning this way can speed up the simulations by several orders of magnitude, and it can be used this way, for instance, to recover magnetostructural correlations in magnetic molecules. All right, so before concluding, I just want to also summarize the entire philosophy of the study here. So the end goal of our research is to discover new molecular magnets, and to do that, you need to take care of all the stages that goes from the understanding the physics behind them, connecting the physics to the chemistry, for instance, by using knowledge from Lughan field theory or crystal field theory that has a very simple chemical interpretation. And finally, machine learning, we think it's going to be very useful in the future to speed up the entire process and discover new molecular magnets. So just let me thank the group in Dublin, Stefano, for setting up this nice series of seminars, and thank you for your attention.
Okay, so let me get back. All right, thanks a lot, Alessandro. So now we have time for some questions, and so as I said, you can post the questions on the dial-up model. Essentially, after you build a convenient representation of your molecule, is essentially a regression. And I just wonder how this method compare to more deep learning methods. So when you use neural networks or stuff like that.
Okay, so let me go back to the model. So you can think of SNAP as a very shallow neural network. So essentially, it's the same as having a neural network with no essentially hidden layers. So this is essentially the easiest representation you can do with machine learning. And since you have a small number of parameters, this is usually very easy to train. And indeed, we saw in this example here, just a few hundred configurations are usually enough to get a very good accuracy. On the other hand, it means that since you have a small number of parameters, you're going to eventually saturate the ability of the model on predicting new values very quickly. So I would say this is very easy to train. You can do it in an automatic fashion, and that would be my first choice if you have a relatively small system or just one molecule or a few molecules. If you're thinking about projects where you have to, let's say, run a regression on the entire chemical space, and you want to include, I don't know, millions of different structures, probably this model is too simple. So you need to increase the complexity and go to neural networks. But in that case, you need to bear that, yes, you're increasing the flexibility of the model, so you have more parameters at your disposal. But this also means that the number of reference structures that you need to include in the model for the training increases. So this means that for this kind of applications here, that you have to run a much larger number of first principle calculation, that it's not always possible, of course. So I would say you need to find the right balance between complexity and accuracy. And for limited number of atoms or species, SNAP, I would say, it's the best choice in my opinion.
Okay, thanks a lot. Okay, I don't see any questions, so maybe I'll ask another one, and then if nobody asks any further questions, I think we can stop here. So, I mean, you constructed a presentation, this bispectral component, which is somehow intrinsically rotationally invariant, but then you go after describing a quantity which is a magnetic anisotropy, so actually is a tensorial quantity. So how the two things can really go together?
Okay, so so what we do essentially, it's like we were training a different model for each component of the tensor, and then we impose the covariancy on the rotation of the tensor. So essentially, yeah, we are essentially extending the model to have more outputs. So we are going to have one output for each components of the tensor, but then we are going to also include, let's say, artificially the covariancy, so the correct symmetry of the problem. So that's how we handle these kind of problems here.
Okay, thanks a lot. Okay, so I don't see any questions, so I would like to, okay, we can clap our hands, but I think we have a lot of virtual clapping here coming up from the blog.
I can hear it.
So thanks a lot for the talk. Now, for those of you are out there, I just would like to remind you that we're going to have another talk this Friday, and so this time we're going to have. Oh, sorry, I have another question coming up. So I just read it out. Is there pre-existing knowledge of bulk magnets that can be used as a guideline for molecular magnets?
Probably yes. I mean, the physics behind magnetism is essentially the same for bulk magnets and molecules. So essentially, you have usually the d electrons on the transition metal and the crystal field that gives origin to magnetic properties. So I would say you can exploit the knowledge about bulk system to select specific molecules. However, I will also say that the number of bulk magnets known is probably smaller than the variability that you have in molecular complexes. So I'm probably not an expert enough to say this, so maybe Stefano, you can join if you want, but I would say that the structures of bulk magnets are going to be always more or less the same, or at least the variability is not going to be very large. But when you go to molecular complexes, essentially you can an infinite playground of coordination environments that you can play with. And probably it's easier to do the reverse. So take a look at what happened in molecules and see if there is a corresponding bulk compound. That would be my guess.
Yeah, I would agree with that. I think if you look at bulk magnet, particularly those presenting high Coulomb temperature, you're always looking at extremely high symmetry structures with typically tiny distortion over the size symmetry structure. Okay, there is another question coming up, and the question from Michael Craig is how many how many k? What is the maximum value of k to get a minimal error in the snap?
Okay, so well, in principle, you can increase k to infinity, and so in that case, you would keep increasing the number of parameters, and at the same time, if you also increase the number of structures that you have in the training set, you can reach whatever small value of error that you want. In my experience, an optimal number for practical purposes is to use a k which is 8 that correspond to 56 parameters for this specific model per chemical species. So yeah, you count the number of chemical species you have in the system, you multiply it by 56, and you get the number of total parameters that you have in your system. Usually, well, you're going to be happy with a few hundred parameters in total. Let's say for a molecule of general complexity, you're going to have 4, 5, 6 elements, so 200-300 parameters. It's going to be enough to get a very good description. But yeah, the entire concept within behind machine learning is that in principle, you can always increase the number of parameters and increase the number of information that you provide for the training and reach a lower value of the error.
Okay, thanks a lot. Okay, so I guess we can stop here, and so let me just remind you that okay, so next Friday we're going to have a. Oh, sorry, there is another question again. A quick comment on the size of the neural network used in the training for the third part, so the snap.
So it's 56 parameters times the number of elements. So it's always a relatively small value of parameters that we have to train. So for instance, I don't know, let me see. Here we have 6, I think, chemical species. So I guess in total we were using around 300 parameters, which is a relatively small number. So if you're used to working with neural networks, it's very easy to get to 1,000 or several thousand parameters.
Okay. All right. So maybe we stop here with a question. And I would say so we're going to have the next seminar next Friday, and so it's going to be Stefano Cultarolo from Duke, who is going to talk about all the A-flow effort in looking at particular disorder, high entropy compound. So let me thank Alessandro again, and thank everybody online for following, and see you all on Friday. Bye-bye.
Bye, thanks a lot.